Hey guys, today's video is going to focus on chemical equilibrium. We're going to take a look at what it means to say, that a reaction is at equilibrium. We're going to figure out how to set up equilibrium expressions before finally shifting focus to discuss Le Chatelier's principle and to see how a system at equilibrium responds when a stress is placed upon that system. So first things first, I think it's important to realize that very few reactions only proceed in one direction, okay? Most reactions are reversible, at least to some extent. We will begin to quantify that extent here in the coming days, okay? I think we're familiar with the idea that we tend to start with reactants and we form products. And that's true, right? That's true to a large degree. For a reversible reaction, the reaction is going to proceed towards the formation of products. That being said, as soon as we have these products in hand, right, as soon as product molecules are formed, the reverse process will actually begin to take place. And we're going to find that we start to form reactant molecules from the product molecules. And we can take a look at that in the context of the following reaction. So imagine that we are reacting water with carbon monoxide to form hydrogen gas and carbon dioxide. Okay, and we're running this reaction in a closed reaction vessel. Now, initially at time zero, we find that the concentration of, say, our water or our carbon monoxide is quite high, right? These are our reactants. And as time progresses, we begin to diminish these amounts, these concentrations, as they look to react to form product. And we see that, subsequently the concentration of our product starts to increase. But eventually, once equilibrium is reached, we find that there's no change in concentration of our reactants or products, right? That the rate of our forward reaction is equal to the rate of our reverse reaction. And we say that this is a state of dynamic equilibrium. So something is happening, right? Reactions are running in the forward and the reverse direction, but these concentrations are not changing. We find that we see this kind of plateau exist, okay? So just to kind of firm that up, again, as far as kind of a formal definition goes, we say the chemical equilibrium is achieved when the rates of the forward and reverse reactions are equal and the concentrations of the reactants and products remain constant. Right? I liken it to kind of a ski resort analogy. You have individuals kind of heading up the mountain, say like in a chairlift or something, and that's going to equal the rate of people actually skiing down the mountain. Right? We got 10 people go up, we got 10 people go down. So it's dynamic, right? There's a forward direction and a reverse direction, but ultimately the amounts are not changing. Okay. Now that is for chemical equilibrium. We can also talk about physical equilibrium. And this is more for processes, things like phase changes, right? So, maybe at 100 degrees Celsius, we say that liquid water is in equilibrium with water vapor. Okay, that gaseous state there. All right, so let's begin to talk about the equilibrium constant. When we talk about the equilibrium constant, obviously we are talking about some type of reversible reaction. We're going to be talking about its equilibrium state. And the equilibrium constant for any reaction, we'll come back to this, is going to be dependent on temperature. And all it is a way to quantify the ratio of reactant and product concentrations. That's it, okay? So if we have a balanced reaction between A and B, yielding C and D, where the lowercase letter here are representing coefficients in the balanced equation, we find that the way to quantify this relationship, right, this ratio of products and reactants is really equal to the concentration of products over reactants, and these are raised to the power of their coefficient in the balanced equation. Okay, and this should seem familiar from your previous chemistry class. One thing of note, and this statement here is incredibly important, we will exploit it kind of moving forward. We find that whenever we have a K value, so this equilibrium constant much larger than 1, that the equilibrium will lie so far to the right that essentially we just, we favor products, and we consider that reaction to proceed at about 100%, okay, in the forward direction. That being said, if our K value is far less than 1, less than, say, 0.1 here, okay, the equilibrium lies so far to the left that we favor reactants, which is to say the reaction essentially doesn't occur. Okay, and again, we will come back to that relationship here in the coming days. I think it's important to talk about the why, right? Why do we actually care about equilibrium constant expressions? And there's a lot of reasons. If you're a synthetic chemist, it's always important to be maximizing yields, right? We don't want to waste our time. We don't want to be wasting money, okay? So to drive the reaction in the forward direction, right, to the right, is going to be incredibly important. Imagine that you are taking a look at some acid-base system, right? You're a physician, and you are working with a patient on different acid-base imbalances. An intimate understanding of the equilibrium involved there of all those reactions is important. Same thing if you were an atmospheric chemist, and we were trying to understand the degradation of the ozone layer and the different gas phase reactions that are important there, right? All these things are in equilibrium, and without knowledge of the different processes, we can't really have a complete picture, okay? So just a couple quick whys. So when we talk about equilibria, we can have what's called homogeneous equilibria or homogeneous equilibrium. And this is where we have a reaction where all reacting species are in the exact same phase. So in this scenario here, we find that both reactants and products are in the gaseous state. So if I want to set up my equilibrium expression for gases, I can do so in two different ways. Okay, so are we discussing gases in terms of their molar concentrations, like moles over liters, like we're kind of accustomed to seeing, right? And that's what brackets are going to indicate. Or are we talking about gases in terms of their partial pressure? Now, if we want to set up an equilibrium expression that's using these molar concentrations, we use the familiar brackets, okay? If we are going to be talking about their partial pressures, we use parentheses instead. That being said, rarely will the molar concentration yield an equilibrium constant that is going to be equal to the equilibrium constant as derived from using partial pressures, rarely. And so in order to kind of convert between them, Kp is going to be equivalent to Kc times by the ideal gas law constant by temperature, and this product right here is raised to the power of delta N, where delta N is the change in moles, right? So the moles of gaseous product minus the moles of gaseous reactant, okay? Let's take a look at a specific example here. So let's say we want to talk about the generation of ammonia in the following reaction here, and we're just trying to come up with the equilibrium expression. So I have my balanced equation, okay, and I know that our K value is going to be equal to products over reactants, again, with those products and reactants raised to the power of the coefficient in the balanced equation. So I find that my ammonia is raised, that concentration, to the power of 2. My nitrogen is raised to the power of 1. I got my hydrogen raised to the third power. So again, if I have brackets here, I'm talking about molar concentrations. That's what that subscript, that C, is denoting there. If, however, I wasn't dealing with molar concentrations and the problem where I was going to be performing some math gave me, say, atmospheres, like I was working with partial pressures or maybe mole fractions and the overall pressure, I'd be dealing with our Kp, okay? Now, again, to convert between them, Kc multiplied by gas constant times by temperature, and this whole product here is raised to the delta N. In this case, our delta N is moles of products minus moles of reactants, where I have 2 moles of products and I have 4 moles of reactants. Therefore, 2 minus 4 is our -2 exponent there, okay? So the question is, what if it's 0, right? If ever the moles of product equal the moles of reactant, when I go to subtract, right, that 0 is going to give me a value of 1 here, and as a result, our Kp will actually be equivalent to Kc. So that's the only time that Kp will actually be equal to Kc there. Instead of homogeneous equilibrium, we can talk about heterogeneous equilibrium, and this is where we're examining a reaction where we have different states of matter. So if we take a look here, we find that we have solid, gas, liquid, and it's important to remember that solids and liquids do not appear in the equilibrium constant expression, okay? It'd be weird to talk about solids or liquids because their concentrations don't change, right? It's an intensive property. It's a lot like density, right? It's not dependent on the amount that you have, okay? So when we go to create our equilibrium constant here, if we're doing so, again, in terms of molar concentration, the only thing I really need to key in on, right, is the fact that I have a reactant in the gaseous state. So my numerator is going to be 1 because I have no product in the gaseous state. The chlorine gas is down low, raised to the power of 6, as dictated by the coefficient in the balanced equation there. If I'm talking about my Kp, again, I'd have to be dealing with pressures like, say, atmosphere. It's going to be pretty popular. I have to be using atmosphere if I'm going to be using that 0.08206 value. So again, same kind of idea here. Okay, let's take a look at just a couple more examples. Few more examples. In this following example here, it's the same kind of idea, right? I have a solid that I'm not really going to be considering. My product is in my numerator, so raised to the power of 1, raised to the power of 2. There's my, my equilibrium constant in terms of molar concentrations. I can do the same thing for my Kp. Again, parentheses as opposed to brackets. I'm going to be dealing with partial pressures there instead, which essentially is, reflecting amounts, right? Reflecting concentration. In this next one, I think this is a really nice example where I have a dissolution process, right? I have solid silver chloride dissociating into its component ions, into the Ag plus and the Cl minus there. Now again, solid, not really concerned about. The only things that really find themselves in our equilibrium constants are gaseous species and also things that are aqueous. So I will consider the Ag plus and the Cl minus, again, products. So in the numerator, technically my denominator would just be 1, not even going to write it in. And again, this is my equilibrium constant in terms of molar concentration. It doesn't make sense to talk about our Kp because we don't have gases, right? We're not going to be talking about the partial pressure of some aqueous ions there. Okay, so keep that in mind. We really got to be having kind of a homogeneous system that's dealing with gases in order to be talking about our Kp. All right, let's shift focus and talk about Le Chatelier's principle. Again, you'll be familiar with this in terms of shifting, right? If we have a system that is at equilibrium and we apply some stress on that system, the system is going to respond in such a way so as to alleviate that stress, okay? And there are 3 different stresses that we can place upon a system, normally towards some desired result, right? We want to form more product or something. And as a result, we can kind of exploit some conditions. The first type of stress that we can manipulate is that of concentration, okay? And there's a number of different ways to think about this. We'll break down 2. If we ever increase the amount of reactant, it should make sense that, necessarily, the reaction is going to want to form more product, right? And we'll be able to verify this quantitatively moving forward. But think of just like a balance, right? And we tip the scales a little bit heavier, in terms of reactant. The system is going to want to kind of, counterbalance that. And as a result, that reactant is going to immediately react and form more product. Likewise, if we increase the amount of product, it is going to want to shift to the left in a reaction, right? It's going to want to reverse direction in order to form more product. Now, these statements here, if in K, we have to make sure we're talking about something that's aqueous or a gas. If we are increasing the amount of solid or we are increasing the amount of liquid, it really has no bearing on the equilibrium constant, so we're not going to see any positions kind of shift, okay? Let's take a look at the following reaction. Let's say, given the following reaction, we are going to increase the amount of carbon monoxide gas. Okay, now gas in this case is a product. So if we want to increase the amount of product, what's going to happen is that the system is going to respond in a way to diminish that product, and it will thereby shift left, favoring the reactants. Let's say we add or even remove solid carbon. Well, solid carbon isn't going to exist in our equilibrium expression, right? So as a result, it really has no bearing on that numerical value. So whether we add it or remove it, it doesn't matter, okay? We're gonna find no change. If it's not part of our K value, it doesn't have any bearing. Finally, if we remove one of the products, it's the same idea. If we were to remove a product, the system wants to respond in a way so as to produce more of it. As a result, we are going to shift right in order to form more of that product there. Okay. The second type of stress we're going to take a look at is that of pressure. And there's a couple ways that we can manipulate pressure. The first is simply adding gaseous reactants or products, right? And this is essentially what we just covered, right? We'd be affecting the partial pressures or the molar concentrations of one of the reactants, one of the products. As a result, the K value would kind of get out of the whack, and we would either have to shift left or right in order to kind of reestablish that equilibrium. The other thing we can do in terms of manipulating pressure is adding an inert gas, right? Something maybe like helium, for instance, that has, again, no place in our equilibrium expression. And if it's not in the equilibrium expression, it's going to have no effect. Because again, we will verify this in the coming days, it's not going to change partial pressures. It's not going to change molar concentrations of any of our reactants or products involved. Finally, the last thing we can do to kind of change pressure is we can manipulate volume. So if we're running this in some type of closed container, we're going to find that if we decrease volume, essentially what happens by decreasing volume is that we find that there's a rise in pressure. Well, the system wants to respond to reduce that pressure now all of a sudden, right? There's like that counterbalance, that kind of pushback. And so in order to decrease pressure, we are going to shift to the side with less moles of gas. In the event there is an increase in volume, which would result in a decrease in pressure, the system will respond in a way so as to increase pressure and thereby shifting towards the side with more moles of gas. Let's take a look at this in practice. The following equation here, let's say we decrease volume. Okay, again, if we decrease volume, given the following equation here, by decreasing volume, we find there's an increase in pressure. The system wants to find a way to thereby decrease the pressure. That's its like counterbalance. Well, we have 1 mole of gaseous product and we have a total of 2 moles of gaseous reactant. So if we are trying to decrease the pressure, we want to shift in the direction where there are less molecules of gas, thereby being less collisions of gas and therefore less pressure. So we will see a shift right here. In the following equation, let's say that we are going to increase volume. We're trying to figure out, well, what's going to be the effect there? Well, if we increase the volume, that means there's going to be a decrease in pressure. The system wants to respond in a way so as to increase pressure. So normally we would shift towards where there are more moles. Okay. That being said, if we evaluate this equation, I have 4 moles of gaseous product, and likewise, I have 4 moles of gaseous reactant. So in this case, manipulating pressure isn't going to result in a change of shifting of the equilibrium. We're not all of a sudden going to start to form more products. We're not all of a sudden going to start to form more reactant. There will be no change subsequently. The last stress that we can place on a system is that of temperature. Okay. Now, one thing of note is that unlike concentration or pressure, temperature actually changes the numerical value of K. Again, something we'll begin calculating here in the coming days. Okay, so keep that in mind. Not only are we going to have a shift left or right, but we are also going to have a change in the numerical value. In order to predict whether there's a shift left or right, we have to have knowledge of the change in enthalpy, right? Does the reaction require energy or does it actually release energy? So if we examine the following reaction, nitrogen and oxygen gas are going to come together in a synthesis type reaction to form nitrogen monoxide. We find that we have a positive value for delta H. If we have a positive value, that means that this is endothermic. Recall that endothermic reactions require energy. So what we're going to do is we are going to write heat, in this case, as a reactant. It is a requirement for this reaction to proceed as normally written. So the stress that we're going to place on this particular system is that we're going to cool this system down. Well, if we cool this system down, the system wants to find a way to kind of battle that, right? And so its way to battle that is to produce more heat. So if it produces more heat, it wants to shift to the left, okay? This would be problematic if we're trying to form more nitrogen monoxide here. So in summary, we can treat heat essentially as a reactant or product. We know whether it is going to be a reactant or product. If we have a positive value for our delta H, it will be a reactant. If it is a negative value for our delta H, we can treat it as a product. And just keep in mind that anything that requires energy, obviously by heating that thing up, we are going to favor that in terms of spontaneity. Anything that releases energy, normally we can favor that by actually decreasing the temperature. We will drive that reaction further to the right, okay? I know I said there were 3 stresses. The 4th one doesn't really count, okay? The last thing we can kind of do, and I think this is a misconception for students, is, what about the introduction of a catalyst? We haven't covered thermodynamics quite yet, but you should recall that catalysts increase the rate of a reaction by decreasing activation energy, okay? That being said, if you decrease the activation energy, say we have kind of a standard exothermic reaction here, and we're going to decrease kind of that activation energy there, you've not only decreased it for the forward direction, you've also decreased it for the reverse direction. And so what we do is we actually increase the rate of both the forward and the reverse directions equally, okay? So we're not gonna find, a change in our K value, right? The equilibrium doesn't shift to the left, it doesn't shift to the right. The only thing that happens is that the equilibrium is actually reached faster. All right, thanks guys.